This video has been supported by PCBWay. Hey folks, a friend rescued this 19-inch white box with buttons and displays on the front from being scrapped. Knowing that I have a thing for boxes with buttons and displays, he offered to donate it for a YouTube repair attempt. The words "OMG, yes please, I'll do anything" were out of my mouth before I even realized that, hey, wait a second. This isn't a Datron 1281 8.5 digit multimeter. This is a 4950 multifunction transfer standard. Okay, that sounds delicious too, but what does it do exactly? Well, that's a bit tricky. You see, it does most of the things that a 1281 multimeter could. Measuring voltages, resistances and currents, but much worse, and at the same time much better. What's worse is that its ranges are very short. In the 10 volt range, for example, you can measure 10 volt and 10 volt only, plus minus a few percent maybe. A 9.97 volt 80 RMU, for example, is accepted, but a 9 volt battery? No, that's out of range. Out of every range. This transfer standard will not measure 3, 5 or 7.1 volt. Only its predefined points of interest. It's a bit of a snob in that regard. A likable one though, because this limitation buys us more and tighter tolerance specifications for those measurements that are available. Let's say when comparing a 100 ohm standard to another, the 4950 gives you a 30-day 3 ppm uncertainty and a 90-day 4.2 ppm uncertainty, whereas with a multimeter, a day after calibration, you'd instantly fall into the 1-year 8 ppm window. Arguably, the multimeter is not going to sit there 23 hours and 59 minutes after its calibration, impatiently looking at its wristwatch, waiting to lose accuracy all of a sudden. If lucky, a DMM can stay within its 24-hour spec for years. But this WaveTech multifunction transfer standard in front of us is not about luck. This kind of fine print in the spec sheet is more catering towards the suit-wearing, spreadsheet-centered bureaucratic side of metrology that needs guarantees to transfer accuracy from one department to another or to a customer without exceeding an error budget, or a budget for that matter. As indicated by the multifunction keyword, this compact box can probably substitute hundreds of thousands of dollars worth of conventional standards. Or at least that would have been the sales pitch back when this was out there on the market. So, in short, WaveTech 4950 is a multimeter that can only measure around certain values at which electrical standards usually exist. It doesn't do linearity with which one could digitize arbitrary values in between, but those ranges that are available do have some pretty impressive specs. So why, pray tell, was it thrown out then? Well, let's ask what its self-test program has to say about that. This is a fairly sophisticated procedure, testing for things like plausible ADC readings at no input, drift of both of the voltage references in here, state of calibration based on memorized data and a real-time clock. It can even conjure test signals to verify its own AC and DC preamps, those ranges, and currents and resistances too. And sure enough, after a couple of runs I did catch some intermittent errors, mostly in the AC department. Now you could argue, hey, at least it's working sometimes. But nah, intermittent faults are not what I like to see. I like to find big, obvious, crispy problems, removal of which makes everything recover magically. No such luck today, I'm afraid. This looks nice and clean. Only all the perishable parts have a little Sharpie dot on them, which I made a few weeks ago to help me order a complete set of replacement electrolytics for this machine. Also a drop-in replacement for the obligatory hygroscopic mains filter, the likes of which tend to become an explosive stink bomb after a few decades. The mechanical construction of this thing seems a bit mad to me. There is a huge amount of custom sheet metal parts and angles and brackets and covers over covers. Little plastic combs that keep the board-to-board interconnects organized. The main power switch is actuated by a control rod that goes through the aluminum extrusion of a sidewall. And of course we can't forget about magnetically arrested folding carrying handles. I kinda love it, but inventory management, all the manual labor and quality control in the assembly also seem kind of horrifying on the other hand. Interestingly, this device has 2 IEC power outlets on the rear, for connecting its calibration victims to. At first I thought one of those 2 large toroidal transformers would be configured in a 1-to-1 configuration to provide some bonus isolation to those outlets, but no, they are just branching off of the main input. So this is purely a countermeasure against common mode effects from less than optimal mains connections. And this is why I preventively swap IEC filters. These epoxy reefer Y-caps accumulate humidity, which leads to leakage currents, heat, and ultimately tar diarrhea being sprayed everywhere. This is the digital mainboard. It's going to get a complete recap, a battery swap, and a refresher of the 2 UV EPROMs which hold the firmware. You've probably seen these standard preventive replacements 100 times before, so I'm going to take care of those in the background while trying to decipher some of the functional principles. That isn't going to be trivial for the analog mainboard and the AC module in which we are most interested in, because schematics or a parts list for the 4950 specifically have never been published. But the front panel, the digital board, the current and ohms measurement assemblies, and the AC attenuator have close relatives in other Datron or Wavetech products. For those, I hope we will be able to find some materials in the vast xdevs.com archives. The digital side of business is centered around a classic Motorola MC68000 microprocessor and a supporting CPLD that can be found, I think, in every single Datron of this era. These 3 labeled DIP parts are programmable array logic, almost FPGAs just without the field. They are helping with memory device selection and just overall device control features. I tried briefly to update the firmware on the UV EPROMs from 2.07 to 2.8, which is available on the XDev servers. Unfortunately, this new firmware refused to work with my old programmable array logic, so I just ended up rewriting 2.07. The very valuable calibration constants are stored in volatile memory, which is made non-volatile with that 3-volt lithium battery. To avoid losing anything, I will swap this battery with a powered-on instrument and an isolated soldering iron. The latest date codes I'm seeing in here are around 1995. The 00 marking on this lithium cell might mean that it was swapped around year 2000, so in a 5-year interval, precisely as per manufacturer recommendation. This swap just now is a teeny tiny little bit overdue though. We are around 18 years too late. Oh well, as long as the data survived. Let's start digging into some of the analog goodness. The current measurement board has this long, unshielded but twisted pair of PTFE cables, bravely leaving its shielded enclosure compartment, and going all the way back into the dirty EMI-infested transformer quarters. I think fundamentally this board is an unchanged inheritance from 1281 multimeters. There have been various trim levels throughout the years, sometimes with exquisite hermetic foil resistors here or there, and sometimes only with plastic molded wire wounds. But functionally it looks like it's pretty much always the same. It's a straightforward current to voltage converter that uses a JFET to normally send its 100 microampere range through a series connection of 900 ohm, 90 ohm, 9 ohm and 1 ohm. So 1K resistance in total, making a full-scale reading come out to 100 millivolt, which is then buffered and passed on to the DC preamp. A JFET is a good choice for switching such low currents, because it doesn't have a minimal wetting current, like electromechanical relay contacts do. There is a pretty significant channel on resistance, however, which is why JFETs can't be used to switch higher currents. The aforementioned fuse detour all the way to the rear of the instrument is connected between these 2 pins. The twistedness of the cable gives this branch what's called a small loop area, and therefore some inherent EMI resilience. The resistors with which this shunt string is built are 3 Vichy VHZ hermetic bulk metal foilers, which the manufacturer calls secondary standards in their datasheet. And then there is one axial, probably HZ series hermetic bulk metal foil resistor, which is even more fancy than the others because it's made from multiple resistor chips in parallel. Absolutely superb components, probably chosen for low long-term drift, as opposed to, say, VHP series, which is, I think, more tuned towards low tempco. HP's and Keysight's 3458A multimeters use much lower quality resistors for this purpose, saving some money but having to rely on auto-calibration to correct for any drift. We've got some remains of a past catastrophic failure on the board here. It looks like these 2 diodes are meant to protect the output buffer in the event of a massive overload. This has been repaired already as far as I can tell, and this node is not particularly sensitive to leakage currents, so I don't think we have to grind away the slightly conductive charred circuit board material this time. Lucky Mr. Current Assembly. Uh-oh, next up is the Ohms measurement assembly. This bad boy is dense and complicated, surprisingly so. 4950's preferred mode of operation, the thing with it only accepting a handful of nice and round standard resistor values, I would have thought made it the perfect place to employ a resistance bridge measurement technique, where it could simply swap in one internal reference resistor per range and measure deviations of externally connected DUTs with its own built-in low-voltage preamp. That's not what Datron's engineers had in mind, however. Admittedly, that would have required quite a few costly parts, but even with their different implementation, the manufacturer still had to throw heaps of Vichy foil at this board. And some other delicacies. This is in fact another inheritance from the multimeter side of the family, which is why we have this lovely block diagram. It shows how an operational amplifier circuit is given the central 0-volt star ground point. And as is an operational amplifier's nature, it will do all within its power to steer its other input towards that same 0 voltage. That way, in 4-wire mode, we always get perfect mecha-centered output signals out of this board, without offsets from test leads, connectors or PCB traces ready for the DCV preamp. But where's the excitement? This has no business being so complicated. I'm glad you're asking. Here are the per-range constant current sources, for which all the precision resistors and their crooked values are needed. In fact, they aren't all that crooked. They are meant to work with an LTZ1000 voltage reference and its typical 7-point-something output voltage. What? Oh no. This is
unacceptable!
So those were just watered down block diagrams. In reality, the innocently looking op-amp symbol titled Low Follower occupies an entire schematic sheet. In the lowest current setting, the I- node is trusted with 10 nanoampere. Depending on substrate and cleanliness, such a low current can easily be overshadowed by surface or interlayer leakage currents, which is why this node and everything associated to it is surrounded by an exposed guard ring on the PCB. The signal on this guard ring is just a local ground, I think, because I- is expected to be around 0 volt. There seems to be a little bit of optional analog filtering. With these two relays, this entire carefully designed circuit can be shown the middle finger, and it can be configured for 2-wire measurements.
Unacceptable!
Over here is a self-cal capability that can place a 100K or a 1K reference into the measurement path. The 1281 parent is titled Self-Cal Multimeter after all. I'm not sure if this function is used at all in 4950 transfer standards though. Haha, maybe we can yoink the hermetic bulk metal foil references without anybody noticing. This relay can detach the current source so that only the raw thermal voltages of an unexcited test setup can be measured and subtracted from the real normal measurement afterwards. As a rule of thumb, one can usually assume that op-amp input terminals don't really source or sink current, but when using signals as low as 10 nanoampere, even those usually negligible effects, like input bias currents and JFET gate leakages, can begin to matter, which is why there is a bias current potentiometer that, in close cooperation with a 68 megaohm carbon composition resistor, counteracts those erroneous currents. Now, I'm on a bit of a crusade against carbon composition resistors. And sure enough, this nominal 68 meg part is over 100 meg now. But when performing a preventive replacement here, we must remember to readjust the potentiometer later. A combination of two different op-amps forms the center of this low follower. There is a popular auto zero part with heavy low-pass filtering. That one is very good at finding, well, DC zero after some settling time. And then there is a fast path.
Fast path!
A low-noise, AC-coupled common source double JFET amplifier, which is going to be very good at getting to the point fast. I don't know why that would be necessary. Maybe 1281 wanted to advertise with fast measurements and convince purchasing departments that that would boost their company's output by I don't know what %. But in case of our 4950 transfer standard, a resistance measurement takes like a minute or so anyway, and that is perfectly fine for getting 7.5 nearly noise-free digits. After having worked on and having left some flux residue and for sure some airborne contaminants on this leakage-sensitive board, I'm cleaning it alternatingly with IPA and a kind of DIY brake cleaner made from 99.9% lab-grade solvents. More about this in an upcoming video where we are going to have to negotiate with leakage currents many orders of magnitude smaller. That video is nowhere near done, I'm afraid. But our sponsor PCBWay has already delivered a fantastic board for the job. This is going to be an attempt at a low noise preamp based on a paper from ETH Zurich. To realize these super fine pitch input guard traces, 2 of which are squeezing through underneath an 0805 package, I had to go right up against PCBWay's allowed minimal clearances, which is an impressive 0.1mm minimal trace width and minimal spacing in their standard process. If you're facing a similar challenge in one of your own projects, give PCBWay's rapid prototyping service a try. And even if you're dealing with something much worse than this, such as a fine-pitch BGA fanout on a limited number of layers, PCBWay still has you covered with their advanced service, where they offer a truly outrageous 2mm, also known as 0.05mm, minimal trace width and spacing both on inner and outer layers. Just for illustration, that is a tighter spacing than the lines on this microscope ruler have. Oh lord, I'm intrigued, but realistically I hope I never have to deal with such a layout. But that is PCBWay for you. Give them a try with the link in the video description below. Of course, the front panel is gorgeous and over-engineered like crazy. Check out the custom, triple-shot injection molded, at least, keycaps. For its mechanical, lubricated, rubber band damped gaming keep. Concise, tactile feedback and lightning-fast actuation of the pre-aged key switches, giving WaveTech 4950 owners a millisecond advantage that matters in competitive voltnutting. There's a little bit of dust in here and some perishable tantalum ticks, but not much else to do today. I'd love to give this meter the Solartron 7081 treatment, and replace what I believe is a Fisher S105 series high voltage circular connector with some proper copper binding posts. Mechanically that would be easy to do, I think, just a new sheet metal part and a front panel segment. But the firmware provides a few special functions for, and gets a bit upset when its special, serial numbered, calibrated 4950 test lead is missing. All of these firmware references to the special test lead would make no sense whatsoever if there were just normal binding posts on here, so I'm not modifying anything today. Maybe I can find such a test lead somewhere. It's almost time, guys. The end of my fake wisdom is near. Because there's only one more helpful schematic out there on the internet for the AC operation in this strange-looking grey circuit board. This must be one of, if not the most extravagant-looking circuit boards I've handled. It's the AC attenuator and preamplifier, very similar to the one that's used in Datron WaveTech 4920 AC measurement standards. Usually, precise attenuation of AC signals is not that hard, because the turn ratio of a normal transformer has no temperature coefficient and absolutely no long-term drift. At least in my transformer experience, I've never seen them lose turns or sprout new ones. But the original design goal for this was to precede AC and DC RMS comparisons. With DC not working very well through transformers, unfortunately, there was no choice but to make this a resistive divider. And for that to have a low temperature coefficient and a low long-term drift, there was no choice but to use fancy hermetically sealed resistors. And if those are supposed to be compatible with higher frequencies, of course there's no choice but to use bulk metal foil technology, which can have this planar, wavy, low inductance pattern, as opposed to wire-wound resistors which can be beautifully stable too, but form literally a coil. And that is, I suppose, how this deranged, super expensive, hermetic bulk metal foil menagerie came to pass. Don't get me wrong, this board is eccentric but absolutely gorgeous. I've never even seen these larger form factor Alpha Electronics metal cans before. But I've got to wonder, the cost of this whole instrument must have been appropriately huge. An entire 3458A is using 0 or 1 hermetic BMF part, and maybe 1 hermetic dip network. But then that is a multimeter, and what we are looking at here claims to be a multifunction standard. So it all makes sense, I suppose. Anyway, this preamp assembly on the grey circuit board is meant to provide amplification from DC to 1 MHz with a superbly flat frequency response, and attenuation up to hundreds of kilohertz with the same requirement, which is why a special high-frequency glass fiber reinforced PTFE-based PCB substrate was chosen. The circuit at large is not that complicated. It's mostly just long series strings of resistors, enabling variable attenuation settings and a bit of independence of any one part's power coefficient. Each of the resistor's metal cans are driven towards a guard potential, using an equipotential capacitive voltage divider, a replica of the resistor strings just made from capacitors, to ensure a somewhat flat resistor to can voltage across the frequency range. That preamp or attenuator then feeds the high accuracy AC assembly, whose job it is to produce a DC voltage proportional to the RMS value of the prescaled incoming AC or DC signal. For that it uses an old strategy that is frankly hard to understand for someone from the just throw a specialized IC at your problem generation like yours truly, but I'll give it a shot. The true RMS value of a signal is defined as the equivalent DC voltage that would cause the same amount of heat in a resistor. It's a popular metric in AC metrology, and we've talked about many methods for quantifying it in the past. For example, literally just building the root, mean and square functions as an analog computer, putting it into a DIP package and calling the whole thing 8637. Or really just comparing temperatures of resistors. The latter still is the most respectable method for AC-DC RMS comparisons today. But good thermal converters are expensive, fragile and need a long settling time. So Datron WaveTech 4950 is proposing the following. Just stop doing AC, guys, it's not worth the trouble. No, that was my suggestion. 4950 uses a logarithmic anti-logarithmic true RMS detector. Its first steering stage consists of 2 NPN transistors and 2 transconductance amplifiers. The tail current or the bias current is going to be adjustable later, but for visualization let's just assume it to be constant for now. This segment presents a high input impedance to a single-ended AC or DC signal, and it translates it into a proportional differential current signal. The second stage is just an emitter-follower that prevents the third stage from influencing the first. The third stage is where the magic happens. So much so that the Teletubby simulator can hardly comprehend it. It's called a Jones cell, and it's basically an analog multiplier for 2 differential currents. That's amazingly useful for mixing purposes among many other things, but in this incarnation, we are simply feeding it the same signal twice, making it square that signal. And that is an intuitively correct step towards our goal, the root mean square computation. Let's express that mathematically. The output is proportional to the square of the input. Now look what happens if we change the 2 tail currents slightly. That seems to change the gains of those differential stages. And so does a change in the resistors. The higher the bias currents or the resistors, the lower the gain. You see where this is going? Me neither. I'm just following the Datron service manual. Next, they derive the bias current from the overall RMS detector circuit output, putting the out term on both sides of the equation and allowing it to be simplified. Because the R's are assumed to be constants, they can just be called away later and don't really matter in a proportionality statement. What matters is that the feedback of the output into the bias currents works like a square root operation in our analog computer and returns us to a somewhat linear response. Now the R and S parts are done for the RMS computation. Adding the M or mean is trivial, it can just be done on a capacitor somewhere. Lastly, the resulting DC representation of an AC-DC signal can be measured normally by the ADC. Theoretically, this circuit is great. It can be made very accurately by choosing well-matched transistors. In practice, in a large series production, it's probably too costly and time-consuming to find the one golden transistor pair out of 100. So to make the design a bit more forgiving, the high-accuracy AC assembly also features an in-house self-calibration function. It's a resistor string DAC, made, you guessed it, purely from bulk metal foil technology. The low-resolution but super stable quasi-sine monstrosity that is generated here is apparently invoked in every single measurement cycle to check and digitally correct for the RMS detector gain, just before it is let loose on an actual signal of interest. Oh, that is so cute. It's low-tech as hell, but for self-calibrations of the RMS detector, it really only matters that it never changes. And it shouldn't, unless the foil voltage divider chain is physically assaulted. This board also features a frequency counter based on this sexy Plessey FPGA, which basically counts 0 crossings per interval and determines a frequency number based on that not bad but also not super nutty 4 MHz crystal oscillator. Why is there no built-in cesium clock in here? Anyway, we have a more important appointment now, with the long-awaited DC or analog mainboard. Oh boy. No official schematics are available for this one, so it might take some actual probing around once I'm done with the routine replacements to find out what is what. But even just looking at the thing powered down, we might be able to make some good guesses, purely based on what this device needs and what we haven't found anywhere else yet. There needs to be a digital to analog converter, of course, to digitize all the DCV outputs of all the aforementioned functions. And for that it needs a good voltage reference. We also haven't met anything related to DCV ranges yet, so I'm expecting some high voltage attenuation and low voltage amplification. And maybe some protection in case somebody accidentally connects a kilovolt to the 10 volt range or something like that. Oh, and most importantly, I'm hoping for some problems. We did have self-test errors after all, without any obvious causes visible so far. Right away over here in the corner, we've got some more of these outrageously sexy, possibly HZ series BMF resistors. They are pretty much the only parts on this board with high voltage clearances. So I would call this the high voltage attenuator. In multimeters you often see a CADOC divider for this purpose. Possibly good, but nowhere near as high quality as hermetic bulk metal foil. These have a custom part number, so they were probably ordered as part of a matched divider set, with instructions such as 10 megaohm absolute resistance plus minus 10%. But matching and temp code tracking down to the last ppm, please. Is anybody else seeing the potential problem here though? These guys have a bad case of the tin whiskers, holy moly. If you've never heard of tin whiskers before, it may sound like straight up science fiction. But here's the living, breathing proof. Pure tin, zinc, cadmium and even lead can, under certain circumstances, sprout long, thin hairs and cause short circuits. Thanks to leaded alloys, this problem has been pronounced cured for a long time. But with lead's ill-conceived cancellation, it might make a nice comeback soon. A short circuit to anything in the high voltage divider would not be good news. But I think the best course of action is just to give these a coarse brushing every decade or so. I can only hope that the casings aren't also tinned internally. The main voltage reference is living in a central mezzanine board. The LTZ-1000A is a bit close to a hot voltage regulator for my taste, but it's got plenty of thermal insulation and it's driven in a temperature coefficient optimized circuit, as opposed to the vulnerable datasheet default. All the crucial configuration resistors that could have an impact on the voltage reference stability are of course superb BMF chips packaged in a hermetic T05 package. These iconic reference modules were used in pretty much every high-end Datron WaveTech product at the time. Even post-acquisition Fluke 8508A multimeters carry this legacy. And 1281 AutoCal multimeters had 2 of them. The 4950 transfer standard in front of us has only one voltage reference module, but one additional LM399 ovenized Zener just for self-testing purposes. On the connector side of the board there is a shielded pair of cables that looks suspiciously like it is trying to smuggle a very sensitive signal along all the busy circuitry and straight into the shelter of the metal can without bumping into anybody. Oh no, please tell me that isn't one of these cursed heat shrink and solder splicer sleeves. Those belong in modded teenager cars, not in legendary metrology artifacts. Oh well, to be honest, I don't see why not. I think this is the direct route to the low voltage DC preamp. This circuit board area below the metal can is shielded with a simple piece of copper-clad FR4. I've already desoldered everything, while zealously looking for more electrolytic caps to replace. And sure enough, there was a grand prize under here. 2 tantrum caps, and most excitingly, a blown 1/8 of an ampere melty fuse. After just having visited the other sections where top dollar Vichy foil is used with reckless abandon, this 2-stage amplifier seems to be surprisingly economic. I'm actually not sure anymore if this really is the one and only DCV preamp, on whose fantastic performance both the ohms and the current ranges depend. This guy doesn't even have any kind of chopping auto-zero mechanism in place, so no countermeasure against the OPA 627's 100 microvolt offset voltage. No, I think this has to be a part of the AC system somehow, where offset voltages don't matter that much. It's awesome to see how these amplifier gains are set by octal thin film resistor arrays though. The central idea of Wavetech 7000 series DCV standards that I ultimately borrowed for my ADR-Mu boards. Hey, maybe this simple fuse replacement is enough to solve our various AC self-test problems. I do enjoy a good round of troubleshooting, but I also enjoy making my videos less than half an hour long. Please leave a comment if you suspect or know what that metal can amplifier is for. This neighborhood fits the user manual description of the DC preamp a lot better. With the 2 stages, the differential JFETs, the CD4047 A-stable multivibrator for the chopping, and possibly the crucial gain setting resistors inside of these early Vishay Golden Boy predecessors. I'll link an EEV block forum thread below where somebody has tragically found one of these beauties with all the previously hermetic ceramic resistor networks decapitated. Viewer discretion is advised. Just behind the metal can lives the one and only multi-slope ADC. That is, I believe it's very close to the one used in 1281 multimeters. So it's not that one and only, but it's a good one obviously. This is the main integrator capacitor. It's a roly-poly, a rolled polypropylene film capacitor with low leakage and low dielectric absorption. This specialized ADC ASIC will take control of these analog switches to initially connect the voltage to be measured to a run-up resistor, transferring charge for a well-known time. Afterwards it connects a well-known reference voltage for a well-known time, steering the roly-poly back to and just slightly over 0. This can go back and forth a few times depending on settings, with slower and more precise slopes every time. The LM311 that is responsible for finding 0 is sabotaged, with a small capacitor on its input, so it will always overshoot slightly. Eventually though, the number of clock pulses that each slope has been active are tallied up, and if all parameters except for the initial signal to be measured were constant, that final number should be very proportional to our initial signal. Yeah, this is not quite as unhinged as that simultaneous multi-run-up, multi-run-down algorithm in 3458As, and it doesn't have to be. This device relies on spot calibrations and therefore has no need for linearity. Only low noise would be good. Let's see if it has survived my intrusion. Oh no, I made it worse. Some harmless little self-test hiccup is now a full-blown no-starter. Well, there is some debugging information at least, and I've read that the 9005 error is often inter-board communications related. But this might be calling for a second video, unless I can magically discover the issue after a good night's sleep, which wouldn't be unprecedented actually. But I also had some experiments planned which would make this episode way too dense. So for now, thanks for watching. More coming soon.